Now, there are a number of different ways one can, in principle, plot binding data to extract these important parameters that you want to get out of it. I'm only going to present three of the most common ways. And mine are only really two of these are particularly common. Third is an older style of plotting. It's not used a whole lot anymore, but you still see it. So you should probably be somewhat familiar with it. So the first type of plot that you see is the so-called standard plot. Right? And this involves plotting the degree of binding versus the concentration of A, straight out, right? Okay, so what would that look like? All right, so if you do that, you would get a plot that looks something like this, where we've got, again, the degree of binding over here on the y-axis, right? And so down here, again, remember we're doing a simple single site binding, go from 0 to 1. Here's sort of the halfway point. All right, and down here is our concentration of our ligand A. And if we look back at that degree of binding expression, remember concentration of A divided by KD plus concentration of A, you can almost predict what this expression is going to, what this plot is going to look like, right? We have it's going to do this, right? So essentially, right, this standard plot, which directly plots that titration data, gives you that nice expected hyperbola, right? That looks something like that, right? Which is great, right? So the most simple, the standard plot's the most simple, direct way to plot binding data, right? You sort of are looking for and expecting something hyperbolic because that's what the equation says you should see, right? So now what do? You got data like this. You did your experiment, right? You did your careful titration experiment, all right? You went and collected your data, used your nice assay, plotted it out, and you get that. Now what do? Well, you should know from the way I've been pushing you guys. The problem sets, the first thing you do is you fire up a nice data analysis package like Ugor Pro or something equivalent. You pump that data in there, you plot it out, and you run a little nonlinear regression to extract out of your fit model for this your parameters, your dissociation constant, right? Where concentration of A is your dependent variable, right? Or sorry, the degree of binding is your dependent variable, your independent variable is A, boom, off you go. Okay, that's great. Turns out there's another way you can quickly evaluate the binding constant, right? If you look right here at this halfway point, right? Think about this. If I think about the degree of binding at the point at which I'm half saturated, right? This is sort of the plateau up here at 1, right? That's where you're fully saturated. You've completely saturated the binding. So at that 50% point, the following would have to be true. 0.5 would have to equal concentration of A over the KD plus concentration of A. Huh. What does that mean? If you just look at that mathematical expression, what would the concentration or what would the KD have to equal in order for that expression to equal 0.5? Pretty easy, right? When the degree of binding equals 0.5, the KD has to equal the concentration of A. Or in other words, the KD is equivalent to, or I should say, the concentration of A at 1/2 saturation, or the half saturation point, is equal to the dissociation constant, right? So at this sort of half saturation point, that concentration of A at that point is equal to the dissociation constant. So by looking at the half saturation point, you can get just off a graph, you can get a reasonable estimate of what the dissociation constant is in the ballpark. It's not the most quantitative way to go about getting your KD, but at least you can estimate it that way, right? Okay, now a couple of things. What happens if your data, instead of going up here nicely like this, what if your data does something like this? What if it's like, right? And maybe that's as far as you can take it out for some reason, right? You could fit that same equation. It would have even actually fit it, right? But do you really have a good estimate of the dissociation constant? You don't know where the asymptote is here, so you can't even do the graphical readout. Turns out the nonlinear fitting is also not going to work very well. So what do you do if your curve looks like that? Okay, this is where the second type of plot comes in for binding data. The so-called titration binding curve or titration binding plot. Right? Which is a plot of the degree of binding versus the logarithm of A. So this is where, again, we're playing with those concentration terms again, right? This is where you got to be careful and remember that technically, can't put a term with a concentration in a logarithmic expression, so it's really the activity. Okay, there are a couple of reasons for doing this, right? And just show you what it looks like. So if you do plot like that, it's going to have a different look to it. So now we're looking at degree of binding on the y-axis. Here we're looking at, again, concentration of ligand, right? Again, we're at 1, .5 and 0. Of course, now, like I said, we're looking at the log of the concentration of A. Or again, right, technically it can't be concentration. As we're playing around with these concentration values and these logarithmic expressions again. So when you do this, you use the log transform of the number, right? What happens to the binding curve is it does something like this. It turns from that hyperbola into something sigmoidal, right? Now, there are a couple of reasons, like I said, for using a titration binding curve instead of the standard binding curve. One is that the sort of issue that I've been dancing around here, this issue of putting a number with units inside a logarithmic expression. Technically, you can't do that, but if you remember our discussion about activities and whatnot, that, if we're going to do this, we have to think about those numbers, the magnitude of those numbers as the activities, so they don't have units anymore. But if we're in ideal conditions, it's basically the same number to a first approximation. And if you remember then, what that would mean is that log of the concentration of A is therefore proportional to log of the activity of A. And if you also remember, log of the activity of A is proportional to the partial molar free energy of A, right? Or it's the extent to which the system free energy changes or is proportional to changes in the concentration of A. So one of the reasons for using these titration binding curves is it's somewhat more fundamental, more thermodynamically correct way to plot titration, plot binding data. There's another reason, a practical reason for doing it, which has to do with that curve. If you look at that curve, what you'll notice is if you had data like I showed you before, this data that's like not quite getting to that saturation point, can't really tell if you've really done the experiment completely or not. If you transform that kind of data into one of these, into a titration binding curve, it gets really clear. Because in that case, your data does something like this, right? Right? At the point where binding should be complete, right? If binding is complete, a titration binding curve, the sigmoid rolls over and you get this nice clear plateau on the top of the curve, right? If your data is not complete, you have not reached the saturation, and this titration binding curve will make that extremely apparent. The curve will not roll over, it'll just kind of keep taking off, and it never quite gets to a very clear plateau. And that's an indication that your binding experiment is less than ideal, and the parameters you get out of it may not be perfect. So while in many cases people will still fit data with the standard plot, it's a little bit easier rather than fitting in logarithmic space, people do both. It still can sometimes be a really good idea to go ahead and plot the data this way to get a look at whether your binding is your binding experiment really spans the space well or not. Okay, the last plot that I want to point out to you guys, that again, nowadays doesn't get in most areas. There's still some specialized fields where this gets used a lot. But for most people doing ligand binding doesn't really get a lot of use anymore, is the so-called scattered plot. Still worth knowing about because it'll pop up in the literature. It's kind of worth knowing what this means. Okay, the scattered plot, this is going to seem a little weird, is a plot of the degree of binding divided by the concentration of A versus the degree of binding. And you look at that and you're like, where on earth did that come from, right? All right, well, the scatter plot fits into a general theme of plots of all kinds of chemical, biochemical, physical data that rely upon a line or transforming data that looks like into something, a model that is a straight line. And the reason for that is, and this may be hard for you guys to imagine, but there was time before these fancy computers and graphing calculators and whatnot, where all people had as a tool for quantitatively analyzing data was something that looked like what I've got here on the screen, this graph paper, right? And if you could figure out a way to transform your data into a line, finding slopes and intercepts could be a really accurate way to quantitate your scientific data. And so that's where the scatter plot comes from, right? Was an attempt to transform binding data into a form that could be plotted on graph paper, and people could use a ruler to find slopes and intercepts. All right, so I'm going to present this, I'm going to convert from the dissociation constant back into the association constant for two reasons. One, it's often, scatter plots are often plotted this way, not always, but some people that still use them will do this a lot. And also because it shows you the form of the binding equation with the association constant, which you will also sometimes see. All right, so let's start with that degree of binding, simple binding equation. Degree of binding is equal to the concentration of A divided by the dissociation constant plus the concentration of A. Remember that the dissociation constant is just the inverse of the association constant, so we can write that as A over 1 over K, and I'm going to use the lowercase capital A, right, plus the concentration of A, which if I now multiply that through, turns into something like this. The degree of binding is now equal to the association constant times the concentration of A over 1 plus the association constant times the concentration of A. Okay, that's great, right? And you can plot this out, and you're going to get a hyperbola, just like we got before. The difference here is that if you only have graph paper, that's kind of a hard thing to deal with, right? So the way in which you transform this into, one of the ways, there are others that transfer this into a line, is to do a little manipulation here. And the first thing you do is solve this equation for solve for Ka times the concentration of A, right? And then use the definition that we've already developed for the degree of binding. And if you do that, what you find is that you can come up with an expression that looks like this. I'm not going to go through it. I'm just going to, it's trivial algebra. Find that Ka, oops, times the concentration of A equals the degree of binding over 1 minus the degree of binding, right? So again, you solve for Ka times A using the definition for the degree of binding, rearrange, you can get an expression that looks like that. Okay, now the thing is, if you multiply both sides of this expression, you multiply this thing through by this, and this is going to seem like it comes out of nowhere, but this is people screwing around until they find factors that would linearize this equation. And it turns out that 1 minus the degree of binding divided by the concentration of A, if you multiply this thing through and then rearrange, you can solve for the following linear transform, which is that the degree of binding divided by the concentration of A equals minus the association constant times the degree of binding plus the association constant. Look at that. Cool, right? It's like, all right, that's y equals mx plus b, right? That's a line with a negative slope. So if you plot that out, again, so now we're plotting out the degree of binding divided by the concentration of A, right? That's our dependent variable versus the degree of binding, right? We end up with something that basically looks like this, right? With a slope that equals minus the association constant, right? Here now is your half saturation point would be, oh shoot. Your half saturation point would be right around here. This would be 0, that would be 1, right? Intercept here on the y-axis, this intercept is 1 times the association constant, right? So you can now get the association constant, or you can rewrite this expression as the dissociation constant, do the same thing, right? And this will work. You can use a piece of graph paper. The problem with the scatter plot, we're going to see an example of this later when we talk about sort of the next level of complexity, or one of the next levels of complexity, when binding events are not independent of each other. We have more than one thing binding. That the scatter plot fooled people a lot, made them think they had a certain type of interaction when it turns out they didn't, right? So this is not the most reliable way. And people are tempted to do this all the time because it's a line. They think they understand lines. But one of the reasons I'm teaching you guys to use tools that do nonlinear regression is this sort of linear transform, in some cases can be useful to illustrate things, but it's not the most quantitative way in many cases to analyze your data, right? And it can distort things and fool you because of the way in which error can propagate through this transformation, right? So still, it gets used to a certain extent, so it's worth knowing about. Okay.